It's really great to be here. Got to get used to this mic. It sounds kind of funny. Okay, so today I'm going to talk about NLP evaluations. I guess I'll give a disclaimer that there are no models in this talk. There is no training. There will be no experiments. I'm just talking about data and how we can convince ourselves that our NLP systems are actually doing what we think they want, what we want them to do. So I guess let's start with SQUAD. For a few, if there are any of you who aren't familiar with SQUAD, this is a data set that was released in 2016 where a machine is given a paragraph of text and a question and is tasked with answering the question, and it turns out that the answer is guaranteed to always be a particular span in the passage, and so the model has to figure out where in the given passage the answer to the question is, okay? Actually, I believe SQUAD was also the first leaderboard, so they started this whole mess that we're in. There are good things about leaderboards too. But anyway, here's the state of the SQUAD leaderboards. I guess there are two of them. There's SQUAD 1 and SQUAD 2. And as you can see here, they measured human performance, and quite a while ago, system performance far surpassed human performance, at least as they measured it here. And so naturally, when this kind of thing happens, you get news headlines that look like this: robots can now read better than humans, putting millions of jobs at risk. But if you ask any NLP researcher, anyone who seriously does this kind of stuff, they'll say, this is like way, way overclaiming kinds of things, because I can take any model on any of these leaderboards, push on it just a little bit, and it falls flat on its face. So here, this paragraph about the matrix, I ask how many people star in the matrix. What I really wanted the model to do was notice that the people that star in the matrix are Keanu Reeves, Lawrence Fishburne, Carrie-Anne Moss, Hugo Weaving, and Joe Pantoliano. Oh, that's 5. The answer is 5. But the model says, oh, hey, you want a number. There's a number in this passage. Let me return it to you. And the problem isn't just with SQUAD here. If you look at basically any leaderboard that we have, here's GLUE, the General Language Understanding Benchmark, which is supposed to test general language understanding capabilities. Human performance has long since been surpassed. Same with SuperGLUE, the next version that was supposed to be super hard. Human performance is basically met. This conversational question answering challenge written by folks at Stanford human performance was surpassed before this paper was presented at its conference, and this happens over and over and over again. And so what do we do? Because people are trying to understand the problem, like why do our benchmarks not really measure what we think they're measuring? If we can surpass human performance without actually solving underlying problems, there's something going on here. So what is it? People have said, well, maybe the problem is with annotation artifacts. Some work here along similar lines. Maybe our data sets aren't measuring the phenomena that we care about. Maybe we're modeling annotator bias. And maybe we're not being comprehensive. Like, there's paper after paper saying, look, there's something wrong with what we're doing here. And I guess the question then is, how do we solve this problem? What kind of evaluation would make us actually satisfied that our machines can do what we want them to do in terms of language understanding? This is a hard problem. I'm not claiming to solve this at all here, but I'm going to present two main ideas about things we can do to fix this. These aren't, I wouldn't say these are new ideas. They're ideas that have been around a long time, but not currently done very well or very often in the NLP literature. So the first thing is to think systematically about the phenomena that underlie the tasks, data sets that we want to do. Take some cues from linguists who do a good job at this. And then the second thing is construct evaluation sets more comprehensively such that they don't have shortcuts in a way that I'll talk about in the second half of this talk. Okay, so what do I mean by like systematic thinking about phenomena? Well, the traditional way in NLP to judge language understanding is to take some formalism from linguistics, like part of speech tags, parts of speech, or syntax where we use dependency parsing or constituency parsing to model this. We annotate a whole bunch of data, and then we see if a model can recover this, and we use its ability to recover these annotations on new inputs as our measure of understanding language in some sense. And this is well and good. It lets us like actually know, can we model certain language phenomena in some ways? The trouble is it breaks down in quite a lot of ways. For example, what about longer structures? I guess we have a lot of linguistic formalisms for sentence level stuff. There are some for broader, like more than sentence level stuff, but they don't typically have very good inter-annotator agreement, and they only give you a very small piece of, say, the meaning of structures larger than sentences. What if we don't have a formalism in the first place? So things like coreference resolution, we have a coref formalism, but if you push on it, there are tons of boundary cases where we know that actually it doesn't really model a whole bunch of things that like the ways that people refer to different things in the world. There are a lot of other places where we really don't have formalisms to model things, not least like semantics, like what is word meaning. Also, making these annotations and then recovering them is one thing. Using the structures that we recover to actually do something, reasoning with them, is another thing entirely that's not tested at all by just recovering some formalism on new inputs. So many years ago, people said, hey, we could use recognizing textual entailment, or what's now called more often natural language inference, as a different way of testing this to try to get past the problems that we saw, I guess the limitations of formalism-based tests of understanding. So this is taken from Ido Dagan and Dan Roth's book on recognizing textual entailment. So here the setup is, instead of taking a sentence and annotating stuff and recovering the annotations, I'm going to take a sentence and then give you another sentence and ask, is this second sentence entailed by this sentence? So John Smith drove to Seattle and bought a Honda Civic. I might ask, is a Honda Civic drove to Seattle entailed by this? And if you look at this, basically to get this right, you need to understand stuff about sentence structure, right? It's the fact that that's an object here, and I'm asking about the subject of drove. I'm using it as the subject of drove. These don't match. And so while this uses a totally different format, it's basically still just querying the same thing as what we queried with our parse. And so if this is where we stop, you might say, am I really getting anything here over just parsing? Maybe not. But I guess the benefit of this format is that I can ask much richer stuff that you can't ask at all with any kind of formalism, such as John was excited about his purchase. I don't think there's any formalism that exists that will let us like annotate this kind of thing on this sentence. And so this is what you get when you move to this other format, right? You would just to be clear, you would probably label this as entailed because of what we know about like John drove all the way to Seattle. When you buy a new car, you're probably excited. So probably most people would say this is entailed. Okay. More recently, we've seen reading comprehension, which I would say is a generalization of this basic idea. Maybe people don't think about it this way typically, but I think this is true. Why? Because we still have some context. Here it's a paragraph, much longer typically than what people typically use as premises or contexts in NLI formats. And we have a question instead of a statement. But it's still the same basic idea. I have two texts as input, and I want to predict something as output. And it turns out that this image comes from Squad. Again, these are examples from the Stanford question answering dataset. And if you look at this question, it's in fact very similar to this original RTE example, in that it's really just querying predicate argument structures again. So what do you need to answer that question? What causes precipitation to fall? If you look at the first sentence, in meteorology, precipitation is any product of the condensation of atmospheric water vapor, so on, that falls under gravity. In order to get that question right, you have to know things about relative clauses and arguments of verbs and so on. We're basically saying, I care about predicate argument structure. I'm going to query it in this particular way using this format. Okay? And so again, you think, okay, I can move beyond formalism-based stuff and query more general phenomena using these natural language formats instead of the linguistic-based formalisms. This is all well and good, but what do you lose when you do this? I think the main thing that you lose is systematic thinking about what's actually going on in your data. This doesn't have to be true, but I think it is in practice. People think, ooh, I'm going to do some like end-to-end question answering something, instead of actually thinking about what's going on. in the data. What is the language that we're trying to actually model here? And so I think to really gain the benefit of these natural language formats, we need to be thinking more systematically about what we are testing in these data sets. And I feel like I'm kind of preaching to the choir a little bit because some of the best work on doing this for NLI stuff comes out of this group. But I'm going to give you, in the rest of the first half of this talk, a case study in how we've been thinking about this for reading comprehension in particular. Okay, so let's go back to SQUAD for a minute. I said that SQUAD largely, at least the example that I showed, looks at predicate argument structure. And I'm going to talk about like what kind of reasoning actually goes on in the reading comprehension data sets. How can we think systematically about phenomena instead of just question answering and thinking everything is the same? So I'm going to use diagrams like this a whole bunch. And so this is just representing SQUAD. So here we have a paragraph as input, a question as input, and I want to predict some answer. So what's actually going on in SQUAD? It turns out that because of the way that it was constructed, it wasn't intended this way, but it turns out that what you have to do in basically every single question in SQUAD is two things. You have to localize the question, essentially find a paraphrase of the question in some part of the passage. And this ostensibly requires probably some kind of like argument structure matching, perhaps, but like essentially paraphrase detection, and then argument extraction. So there's a WH phrase in the question that identifies some argument around the part that I've localized, and I need to pull that out. Again, predicate argument structure kinds of stuff. That's basically everything that's going on in this data set. It turns out, though, that a lot of the time, also because of how the data set was constructed, you can skip the first step. And because the WH phrase uniquely identifies a single type of thing in the paragraph, you can just skip straight to the extraction. And so to correct for this, the authors released SQUAD 2.0, which says sometimes my question might fail to localize. I might ask a question that isn't answerable in the question because of a failure to localize by construction. This is how it turns out. And so then you have to recognize that, and then you can't extract the argument. Okay, but still, they're just two like reading primitives, you could say, in this data set. Paraphrase detection, or localization, and argument extraction. So even if we're talking about like sentence level linguistic structure, SQUAD just like scratches the surface here. There's a whole lot you could do. There are a lot of other kinds of local structure that you could query in this same format that just isn't queried by SQUAD. And we could also think about like more comprehensive tests of the ability to recover sentence level structure more broadly across the entire paragraph. And so what we did was we said, I want to actually test this. Let's build a data set targeting specifically this. And so what we built was called DROP, Discrete Reasoning Over Paragraphs. Yeah.
So you talked about localization.
Uh-huh.
I'm wondering what exactly is localization value on our systems, and is it actually necessary? Like, can SQUAD just give you the exact sentence you ought to look at and skip the localization part? Does that add some value?
Determining that sentence is what I'm calling localization. That's the like you have a paragraph, you need to find what part of that paragraph the question is querying.
In terms of trying to figure out what our systems understand, what is the localization aspect of the evaluation?
So I'm not explicitly evaluating localization. I'm arguing that that's one of the two main like primitive operations that the model has to do in order to answer the question. So I'm not sure I'm understanding your question correctly.
I guess when we think about RTE, right?
Uh-huh.
There's no localization. So it's more straightforward mapping into predicate argument.
Okay, so like when I talk to Sam, he says, well, I'm interested in NLI, but with bigger contexts. So there's nothing inherent about NLI that says I have to have a single sentence. I could have like a bigger paragraph that then I would require localization. Fair enough? Okay, so so we built a data set that again is targeted on like more broad coherence of sentence level structure. And the way we did this was we took paragraphs from Wikipedia describing American football games. And So there are things like field goals and touchdown passes and touchdown runs, and we might ask a question like, which kicker kicked the most field goals? So here, what you have to do is find the event that this is describing, localize it, in some sense, to several different parts of the paragraph, extract arguments from each of those parts, and then aggregate them in some way. Does this make sense? If you're familiar with this data set, you might have heard it described as a numerical reasoning data set. I prefer to, that wasn't our intent. Our intent when we built this was to test predicate argument structure more globally across the paragraph. To me, this is a predicate argument structure data set. If we think of this in terms of our reading primitives, it's still the same too. We just take the question, we localize it to a part of the paragraph. Turns out it's multiple parts by construction, because that's what we wanted to target. You extract arguments from each of those, and then in that final step, there are some reasoning primitives, like there's numerical, sorting, whatever, that I view as a kind of a necessary evil in order to really probe this kind of stuff that I really cared about. Does that make sense? So still, same format as Squad, testing something very different. Okay? So there's sentence level structure. Not at all the end. There's a whole lot more that we could do here, but there's also a whole lot more than sentence level structure that we could look at. There's discourse structure, tracking entities across a discourse. Discourse, like how do sentences in a discourse fit together? Is the discourse coherent? Did the author achieve its communicative goals? All of these kinds of things. There are, again, lots of things you could query. We picked one. We said, let's see if we can build a data set around tracking entities through a discourse. We called this, this might sound like coreference resolution. Indeed it does. We called this data set QuoRef for something like question answering based coreference resolution. And here, this might be a little small, sorry. We took paragraphs, again from Wikipedia, and we asked questions. We came up with a process to get people to ask questions that were targeted at coreference resolution. So in this case, what are the names of the sport that is played in a tsakanasterion? So here, again, it localizes to a particular part. Pretty easy to do that. It's asking about this green part here, that a tsakanasterion is a stadium for playing the game. Except if you notice when I try to extract the argument, it's the game, which is not the name, and I have to follow a coreference chain from the game, polo, and tsakanion. And so that's what we're getting at. And again here, I mentioned something like, what if you want to reason with the outputs of some linguistic annotation? This is more than just coreference resolution. You need the coreference chain, presumably, in order to answer this question. But we're pulling out some piece of the coreference chain, which is the things that are names in that chain. So, yeah. Mm-hmm. Good point. Excellent. True. Yeah, so very good point. Good catch. And we tried, so this data, any data set collection that you do is going to have these kinds of shortcuts. The second half of my talk is targeted specifically at how to fix that, and so we'll come back to this. But even on this one, we did some tricks to try to minimize that. We didn't, as you see, we didn't do it perfectly, but we tried. One thing that we did was we ran, as people were writing questions, we ran a baseline system that could exploit the shortcuts. And we said, if the system gets it right, you're probably asking the wrong kind of question. And so we were trying to use a system that could exploit shortcuts to teach people about what kinds of things to avoid. So we tried. Again, it's not perfect. It's better than it could be, but you're right. And we'll get to a more satisfying solution in the second half of this talk. Okay, so if we think of what's going on here in terms of reading primitives, as we've been talking about before, like what phenomena are actually being targeted here, again, there's still localization and argument extraction. It's just that by construction, most of the time, when you extract an argument, the argument that you extract needs some kind of resolution. You resolve that argument to some other part of the paragraph and extract an argument there, possibly. Okay? So same format as Squad, same inputs, same outputs, very different phenomena. Okay, what else? There's a lot more than just sentence level structure and discourse. Oops, am I going the wrong way? Okay, here we go. I was showing some more examples. Okay, We can move on. There are more examples that you can see in the paper. What else is there? There's probably some linguistic term for this that I don't know. I'm going to call it implicative meaning. So this is like, what things do the propositions that I see in text imply about what I might see next? So for example, if I read that Bill loves Mary and that Mary was just diagnosed with cancer, what it means to understand those two things is to also understand that Bill is going to be very, very sad. Where does this come from? I guess a linguist might say that this is like part of our common sense, which is maybe stored in the lexicon of the lexical entry for love, perhaps. So I don't know, maybe you could build a data, if you want to test this, maybe you could build like some kind of common sense data set that asks this kind of question. This is hard and like very, very broad scope to query this kind of thing. So we took a narrower slice of this and said, well, there are lots of cases where we write down in language these implications. So let's see if we can build a data set that will require us to read implications and then use them. So like causal if-then kinds of language. So what we did was we took paragraphs from science texts. This one describes pollination in plants, that wind and insects are pollinators. One of them is more efficient than the other, and because of this, there was some evolution that happened to attract the more efficient pollinizer. So it's complex language. There's no actual direct if-then, but there are causes and effects, the pollinizers and the fertilization and the evolution here. So we took these paragraphs and we had people on Mechanical Turk instantiate either the causes or the effects in some way. And so here, this story says that John visited a national park, saw two different kinds of plants. One of them used wind to spread its pollen, the other one used insects. And then we had the person also write questions that queried the effects if the situation was about the cause. So which type of plant has more efficient fertilization? If we set this up right and there aren't shortcuts, then what you need to answer this question is to understand the causal language, the implications from the background, and apply it to the situation in order to reason about what's going on here. Does this make sense? I guess, again, if we did this right is a big if. We tried hard. One way that we tried to avoid shortcuts with this data set is that a lot of the questions here have two plausible answers, and we had people change the question. And so as they were writing it, they gave us two versions of the same question, basically, one with each answer. So here the answer changes. So the answer is more. This particular one, we might switch the order of category A and category B so that the answer changes to less. And so you actually have to reason, like you have to figure out the reasoning chain in order to get both of those right. Okay. So this is another slice, another phenomenon that you might care about in terms of general language understanding in some sense. So same format, very different phenomenon. I could talk about this in terms of like reading primitives. It gets a little complicated to actually write down. So I'm just going to say, basically, you add one more primitive that's something like chaining. I need to chain from a cause to an effect to see its influence on the answer options that were asked about. Details here aren't too important. But what other kinds of phenomena are there? There are still more, of course. So time, temporal ordering of events. How long do events typically last? What things are events in the first place? All of these are definitely a key part of what it means to understand, and not queried at all in something like Squad. And so we said, let's build a data set around this. This one's in progress, should be released very soon, maybe within a few weeks. And what we did was we took sentences. In this case, most of them, I think there are 2 sentences in the data. Here I just am showing one. And so this is about a House Judiciary Committee meeting. And I might ask a question like, what things happened before the president was accused? So getting this right requires, first, knowing what things happened. Abuse here is a noun, but it describes an event, like something that happened. Power is also a noun, but it's not really eventive. So you have to know like which things are events. You have to then know what the temporal order of stuff was. So this accusing event happened before almost all of the other events that are mentioned. And note that the occurrence order of the events in this sentence is very different from the linear order, the appearance order of those events in the passage. And so there's actually complex stuff going on here to figure out what the answers are. Another interesting thing to look at is what things haven't actually happened yet. The accusing hasn't happened, and you only know that because of Wade. They weighed articles of impeachment accusing President Trump. So they've only weighed it, they haven't actually published or submitted or approved them. And so the accusation, in some sense, hasn't happened yet. And you only know that because of your lexical knowledge about what it means to weigh. Similarly for girding, it's only because of what girding means that you know that the debate hasn't happened. Yeah.
The part subtle things like, when you say what things happened ended before the parties girding for debate, the only thing that happened is an accusation. The other things, abuse, obstruction, are part of the accusation. At what point do you say they ended or they even happened?
Fair point. There are a lot. Agreed. There are a lot of things going on here about if I'm talking about events that are hypothetical, then things get messy, and I would say this is a benefit for this kind of natural language querying of this stuff because it gets really hard to actually formalize something and write it down. I don't think we have the final answer here at all. But I do think using natural language, you can actually query this a little bit better than you might otherwise. Does that mostly answer your question?
No, what I'm
Is it non-answer?
The question, because if you think the question that what things, maybe must have ended, so in some sense, you're not making a statement of whether or not they happened, but if they happened, they must have ended. I don't know, I just feel that this whole field is so, full of perils that I don't want to pick on this particular one, but this jumped out right away.
I agree that there are definitely issues. I would argue that this is probably better than if you don't think carefully about this stuff, then you have no hope at all. And my argument here is that previous reading end-to-end QA something. If I build a data set without thinking about this, it's going to be worse than what we have here. I'm not claiming to have solved this problem. It's really messy.
Something about the previous example, go back to it for a second.
This one, yep.
So by using fertilization in the question, you made it easy for us to see what reasoning over paragraph needs to happen.
True.
It's all self-contained.
Mm-hmm.
If you just replace fertilization with pollination, more or less efficient pollination,
mm-hmm.
all of a sudden you have one more jump to make, namely that pollination is a form of fertilization.
Mm-hmm.
Or even worse, I said efficient sexual reproduction.
Yep.
And so basically, this is a never-ending thing.
Agreed. So we analyzed that particular gap, how much is there direct lexical overlap versus some kind of common sense jump or paraphrase or whatever in this data.
Versus some even deeper jump
Yep.
which requires background
Yep.
knowledge.
There are some that have exercise and going to the gym. So there are instances in this data that have very, very large gaps that you have to jump. And so yeah, some of them are direct word overlap here, but there's a range of stuff that actually happens in the data we collected.
So we're going to stick with things which are within, if not direct lexical match, there is something in the paragraph itself which might even hint at a match.
Yeah, and honestly, for solving a reading problem, for me that's desirable, because even with this close overlap, there are still hard problems to solve here, and so I'm trying to simplify this to a particular thing first, and solve this problem, and then there are all kinds of common sense, more abstract reasoning. There's a lot to do. Okay. So here's time. If we think of this in terms of reading primitives, there's still localization and argument extraction. Now I have to do what event detection, what things are events, and I have another primitive on temporal comparison of events in order to do some kind of ordering. Yep. Mm-hmm.
So it goes back to so I would
Fair point. I perhaps used too fuzzy an example because the accusation in some sense already happened, but it hasn't happened officially by the Judiciary Committee. Like language is messy. And I think your underlying question is like what is common sense versus this other stuff?
Well, I guess what I'm getting at is that I feel like if you give anything, a computer or a human enough examples of this type of question, they'll figure out like the level of common sense versus is this a very technical question or is it very loose language, right? And like I kind of wonder when you're comparing machine to human performance, is it just that the human hasn't been given a bunch of examples to see the types of, you know what I mean? Like the kinds of answers you're expecting.
I guess when we measure human performance, we typically have the dataset authors themselves be the ones that are tested on the test data. And so you assume that the human performance is actually expert, like understands what's going on and doesn't need all the examples because they like designed this whole system in the first place. And so you're right. Like if there were a few questions in here. I'm not sure I'm answering the right one, but if I'm saying like human performance on Squad, where they took people on Mechanical Turk and had them answer stuff, that's a very different measure of human performance than having the experts who design stuff measure human performance. And I would say we should definitely be doing the latter. Have the experts be the ones that we're measuring human performance against. Okay. So I mentioned, I guess the underlying point here is that we should be taking inspiration from the systematicity that linguists have in approaching language phenomena, and like be sure that we are testing all of the things that it means to understand language. We shouldn't be just deep learning people with hammers and don't really think about our data, because language is hard and has a whole lot of stuff going on. And if we want to actually understand, make claims about understanding language in any kind of like language in, language out kind of setting, we have to be systematic about how we think about what's actually going on in our data. And I gave you some examples. There are tons more. Okay, so one thing that's not incredibly satisfying about this kind of approach is that if I just carve out one slice and I build a system that can solve that one slice, one particular phenomenon, maybe I've just overfit to one particular thing and I don't actually have a general language understanding system. And so one way to solve this, doesn't get all the way there, but at least gets us farther, is to put all of these slices, all of these different phenomena-specific data sets together into one benchmark. And so we've put together this thing that we're calling an open reading benchmark, which is essentially an evaluation server where you submit one model and we evaluate it on all of the data sets that we have at the same time. And so hopefully in that way, it's harder to like overfit to the quirks of a particular data set, and you can test to see if this model actually understands all of the different phenomena that you want to query. And our intent is for this to be open, to grow over time as we and others build more data sets that fit the phenomena that we're restricting, the format that we're restricting ourselves to, which is Squad-like. So I get a paragraph and a question as input, and you can produce whatever output you want as long as we can evaluate it. Yeah, this is available now. There's a leaderboard you can submit to. If you're interested in like reading comprehension research, I don't know of a better evaluation than something like this right now. So we're including all of the data sets that I described so far, also Squad, because Squad does test predicate argument structure. We shouldn't forget about doing predicate argument structure when we move to new data sets. We should be able to do more complex drop stuff while still also being able to solve Squad. Yeah.
Now you have multiple evaluation metrics, wondering what's the right way if you are forced to
Yeah.
show people.
My opinion is we have this average only because we have to rank these somehow, and really that average is meaningless. It's totally arbitrary, and I don't think you should focus on the average. I think you should get insight from the performance across the whole suite of things. Okay, that's the first part of my talk. So again, we were just trying to think systematically about what's going on in our language, because language is interesting and has a bunch of stuff. But the problem is we often end up testing things that we don't actually test. Testing things that we don't think that we're testing. Maybe I'm saying that wrong, but whatever. You've seen an example like this before. I guess the main point is that we often have reasoning shortcuts. So here, if I get a question like, what year was the matrix released? On this paragraph, I see that my system answer is 1999, and I think, yay, I understand language, right? I was able to recover this. And then you start changing the question, and you realize that there are a whole bunch of different questions that get this answer right for totally wrong reasons. So what happened? What happened was that the model learned that there's this association with year, where instead of looking at anything else in the paragraph, I just look for something that looks like a 4-digit number, and I return it. In other words, the model was able to learn a very simple decision rule that performed well on the test data without actually recovering what I wanted it to recover. Again, it's not just squad. This is from Sachin Gururangan's annotation artifacts in NLI paper. It's a messy table. The important thing to realize is that they found that there's a high correlation between the words sleeping and cat and TV with the contradiction label in SNLI. And this is not because there's any particular correspondence, any particular significance of those words to the phenomenon of entailment. It's just some random thing that happened that there exists this correlation in this data, even on the test set. So it means that there's, again, a very simple decision rule that I could learn from my training data that generalizes to my test set. Sorry, I probably should have not worried. This is trying to measure PMI. The detail isn't important. The important thing is this is PMI, top word by PMI. The percent is how much it actually appears. Sorry, I should have picked something else. The main point. There are these annotation artifacts. People have published a lot about this, as I've said. And I guess the language that we use to talk about this isn't really clear. What is an artifact? What is annotator bias? What's a spurious correlation? What does that mean? If we don't know how to, we won't know how to solve this problem until we really understand what's going on. So here's an attempt to try to formalize what is happening so that we can try to solve this problem. And to formalize this, let's talk geometry for a little bit. So here's some data. Blue is positive, orange, marigold, whatever, is negative. And let's say I have some test data that I'm going to outline in red, also from the same distribution of stuff. So if I take this data and I learn a decision boundary, pretty easy to learn a decision rule that looks something like this. Everything above is positive, everything below is negative. And turns out this decision rule generalizes perfectly to the test set. This is great, right? Until I tell you that actually this data collection process had systematic gaps. We only sampled in particular places with some regularity, and if I actually filled in the whole space, I get something like this, and I see that my decision rule totally fails. And it should have been something that looks like this. Note here that this is both a training and an evaluation problem. So I'm going to argue in a minute that this actually happens for NLP. For now, let's still just think about this toy problem, like what's going on here. So the training problem is, given data that looks like this, how do I recover a decision boundary that looks like this? This is very hard. I'm not going to try to solve this at all. But there's another problem, which is an evaluation problem, which is my test set told me that this simple decision rule actually generalized because I did IID splitting of my biased data collection process. So how do we solve this evaluation problem? Ideally, we'd just densely fill in the whole thing. We'd have a data collection process that didn't have these systematic gaps. If you can do that, great. I would argue that it's basically impossible in NLP. So let's say, what else can we do? Well, what you can do to improve this is to take particular test instances and densely sample a region around that particular test instance. So in our toy 2D example, this is like an epsilon ball around a test instance. I'm going to sample as much as I can around that ball and add those instances to my test set. And now this does two things for us. First, it tells us that our simple decision rule clearly fails. It also lets us give a better evaluation metric that I think more closely matches what we actually care about in NLP, which is not overall aggregate accuracy. It's how well does my model actually capture the local decision boundary that a human has for this data point. And I'll explain this with an example, but basically, if I perturb an instance, a person can say, how should that actually change my output space? And that is essentially defining phenomena. And if I measure how well my model aligns with that set around that instance, I'm actually measuring, does my model capture the phenomena that I care about? Which, again, I would argue is a better measure of how well our models capture phenomena than any aggregate statistic that we can compute. Yeah.
So this solves the evaluation problem, but it doesn't solve the, do you have like any, I mean, if you think it's totally impossible to get the training data to actually find the true curve, then you should quit.
I don't think it's impossible. So that's not the focus of this work. I can point you to a few papers that do something good here. At least are starting to think about this. There's, I think it was rejected from Eichler. There's a paper called Adversarial Filtering Light that essentially tries to find dimensions in NLP along which you have this and reduce the training data so that you don't have these correlations. I guess, okay, so for NLP, I've given this toy example. For NLP, what happens? Like, we really have a high dimensional space, a very, very, like, exponentially large space. And we don't see these gaps everywhere, but there exists some dimension along which there is something that looks like this. This is like amply demonstrated in the published literature, like the year example, the SNLI examples. That is what's happening here. There is some dimension in this very high dimensional space along which there exists a simple decision rule that generalizes to test. And so to fix the training problem, what you do is you try to find those dimensions and remove the training points or change the training points in some way along that dimension such that you don't learn that decision rule. And you can still learn the more complex decision rule from the other dimensions. Like, it's a very high dimensional space. You just have to remove these crazy things from single dimensions. So that's one piece of work. There are others. But again, that's not what I'm trying to talk about. So I would argue this phenomenon is unavoidable in NLP because we have this exponentially large input space. There will always be dimensions along which there exist these simple decision rules. And if we split our data IID, then the simple decision rule will generalize to test. And so how do we fix this? With this method of filling in these local gaps around individual test instances. But again, because this is a very high dimensional space, it's not really clear necessarily how we do this for test instances. So I guess the basic idea is to have an expert who understands the phenomena that you're trying to model make changes that make a test instance cross a decision boundary to try to characterize the local space around this instance. This will be more clear with an example. So here's an example from the natural language visual reasoning dataset. Here I get two images. These are two dogs, I guess two images with pairs of dogs, and I get a label like two similarly colored and similarly posed chow dogs are face-to-face in one image. This is a caption that is either true or false about these two images. This image has these two dogs, and so the label is true. Okay, so how might I change this to make this instance cross a decision boundary in some local space? So pretty simple. I change chow dogs to cats, and now my label is false. Or I change 2 to 3, and now my label is false. Or, getting a little bit more interesting, I change similarly colored and similarly posed to differently colored but similarly posed. Okay. I can also change the image. In the text examples that I showed, it was easy to think about like making small changes, like maybe taking hints from linguists about minimal pairs kinds of things. It's a lot harder to think about what that means for an image. In any kind of input pixel space, these two images are quite different from each other. But in like some person's conceptual space, they're actually pretty similar. They're both two dogs that are facing each other. They're just different kinds of dogs. And now this is they're no longer similarly colored, and they're no longer chow dogs, and so this label is false. Okay? So I can make these changes on my data, characterize the local decision boundary around particular test points, but there's still kind of a question, like, how do I know what changes I should make? there's this whole adversarial example line of work that says I should make a change such that a model changes its prediction. That's not at all what we're doing here. We're saying we should make changes that a human thinks are semantically relevant without consulting a model at all. And what change? Well, what phenomena was this data set trying to capture? I spent the whole first half of this talk talking about we should be targeting specific phenomena. If you have a clear idea of what you want your model to capture in a particular data set, that gives you the kinds of things that you should be making changes for here, right? So NLVR2, this data set was trying to capture things like spatial relationships, counts of things, attribute descriptions, and so those are the things that the expert who is making these changes should change in order to construct these like diagnostic, what we call contrast sets. So I guess the key point is you're the dataset author here. You understand, hopefully, what it is you're trying to create. And so you should try to create a test set that would convince you, if a machine could pass all of these instances, that the machine actually models the phenomena that you care about. Hopefully this makes sense. So what we did on this data set, we made these perturbations 1,000 times, getting the original data set authors to do these kinds of changes. We did it for 479 original test instances, and on average, about twice per example. So we had 3 examples on average for every original example, but the original and 2 changed instances. This isn't it's not a particularly dense characterization of the space, but it's what we could do with our limited annotation time, because these were experts doing it. And I would say it's sufficient at least to give us something interesting. So if you look at the accuracy on those 479 examples, so this is, I guess I do have one experiment here. But this model was already trained. It was trained on the original data. All we're doing is evaluating it in some different ways. So its accuracy on those original 479 instances was 76. If you evaluate it on the 1,000 that we changed, using just average accuracy over all 1,000 instances, you get 61. What this means is that the model, and also I will note that if you have people answer both of these questions, they get the same accuracy. So the model has picked up on some dimension in the space that gives it a simple decision rule, and when we have decorrelated the test label with that simple decision rule, accuracy goes down quite a bit. Yeah.
Do you think this picture subset should it only be used as an evaluation set, or should it also be part of the G also?
If you do it at training time, you run the risk that you will introduce another such spurious dimension. We are only doing this for test data. There's an argument that if I do it for training also, I can be more robust. So there was a paper called Learning the Difference That Makes a Difference that did something very similar for simpler tasks like sentiment classification, and showed that if you do similar things at training on the training set, you get better generalization. So there is room for this, but again, that's not the problem I'm trying to solve here. And if you do if you do this for the training data, you at least run the risk that you will introduce more artifacts yourself. Yeah.
And I could go back and get them much more, with much higher accuracy. It's sort of related to the just trickiness of language, but also this training question where a system's trained to sort of trust the integrity of or the good faithfulness of the person writing the test.
So
that's an unfair assumption.
Yeah, I guess our answer to that is we measured human performance on both of these sets, and they were essentially equivalent. Which gets to your point. It's not exactly the point, but it gets there. Am I supposed to stop right at 1?
No, we can go there.
Okay, I have just like a few more minutes. Okay. Okay, so accuracy drops if you measure just aggregate statistics on this 1,000 points. But to me, the much more interesting measure is how well can I capture all of these 3 instances at the same time? Is the model actually able to change its predictions based on my perturbations? And that's what contrast consistency here is measuring. Of those 479 examples, what percentage of them do I get all 3 examples right? The original test instance and both of the perturbations. And again, this is just on average. Some have more, some have less. Okay? And how well? Like 29%. Dramatically worse than what we would expect if we were just looking at this number.
You did get
consistent, you only get a 1 here if you get the original example and all of its perturbations correct.
Okay. So of the 76 that you were getting right in the first instance, less than a third.
Less than a third, you actually also get the ones that we changed. Yeah. Okay, so we didn't just do this for NLVR2, we did it for 10 different data sets, spanning a wide range of NLP stuff. Some classification stuff, all of the reading comprehension data sets that I talked about. In this case, trying to actually make changes to solve the like polo question that you were asking about. So this is my answer to that question. Okay.
Again, there might be some superficial baseline that doesn't give up. So you take a natural occurrence and alter it.
Mm-hmm.
So that's not a natural occurrence anymore. And maybe a language code might pick that up.
I mean, if you look at this example,
Yeah. Who says differently?
I get your point, but still, you could answer this question. And again, our answer is the same one that I gave to Matt, that the person actually answers both.
Like, this is a hard description for the label.
Except the counter argument is the person can, in fact, get this right. And so you would think that a machine that actually understands the phenomenon should be able to get it right, even if there were some quirks. And again, those quirks are why I say that you probably shouldn't do this for training data also, because you could just give the model more signals. Okay.
You probably said this with the human contrast accuracy is 100% as well?
So we did not get 100% accuracy on this, but we measured performance of the people on the original test set and our changed examples. And whatever that number was, it was similar across both. Okay, so on all of these data sets, you can see that if we measure, again, just the test set with an aggregate accuracy statistic, the model does significantly worse, meaning there is this bias problem across a lot of these data sets. But again, more importantly, the consistency is dramatically worse on basically all of these. I want to focus in the last minute or two on this dependency parsing result. So this is universal dependencies, English tree bank stuff. It's looking specifically at part of speech attachment ambiguities. Prepositional phrase attachment ambiguities. You would think that dependency parsing, this is relatively well solved at this point. Numbers are in the high 90s. If you look specifically at prepositional phrase attachment, like this, what should with attach to? Should it attach to demanded or talks? We run a parser, and then we look at just the parser's decision on that particular attachment, and we say, does it get it right? So here in this case, it's the talks that are with local commanders, and it's not the demanding that was with local commanders, and so the attachment should be with. So what we did to do these perturbations in this case was we changed the prepositional phrase to change the attachment. So no longer they demanded talks with local US commanders, but they demanded talks with great urgency. And now it's the demanding that has great urgency and not the talks, and so the attachment decision changes. So we do this with a bunch of examples. The accuracy on the original data, there were only 170 of these, it was small. So it's a biased sample, don't take these absolute numbers too seriously. But our accuracy was 64. When you change it, the accuracy is 46. And if you think there are really just two plausible attachment possibilities here, and you think about those numbers, it basically means the model is not changing its prediction at all, hardly, when we change the outputs here. And our contrast consistency bears that out. You get 17% consistency, where the model is actually able to get both of these right at the same time. So let's think about what that means. Basically what it means is that the model has some bias of attachment between the noun, the verb, and the preposition. So for with and demanded and talks, it thinks talks attracts with more than demanded, and so it always just goes to talks no matter what follows with. That's what's going on. If the model isn't able to change, that has to be what's going on. So the model has some bias that's associated with each of these trigrams. Turns out trigrams are rare. Basically, no matter how big you're going to make your test data, parsing is hard to get test data. No matter how big it's going to be, you're not going to get both. You're not going to see this trigram with both of these different attachment decisions. So without this kind of evaluation, I don't know how we even detect this problem. I think we have to do this kind of thing. IID does not work. We have to do this if we really want to know, does our model understand this attachment phenomenon? Okay, that's it. To conclude, I think we have a very serious evaluation and data crisis in NLP right now. We get numbers that say our models are matching human performance, but no one actually believes them. We need to solve that. And I say, to solve them, we should first think, I guess, take a cue from linguists and think systematically about language, because that's what we're studying, and what is actually going on in the language. And then use these contrasting examples to measure how well our model actually captures the phenomena that we care about. And that's it. Mm-hmm.
And I think that, like, as a human, it would be really odd if humans that development.
Mm-hmm.
I think most of our NLP models would not be good at figuring that out.
Mm-hmm.
And I was wondering if there's any ways of, like, incorporating that into the evaluation if you really want to get at, like, true comprehension. If you comprehended that happens, you'd be able to say with confidence that that's relevant.
Yeah, so Squad 2 basically tries to get at this. It adds questions that have no answer. I think this particular example is probably farther away than they would get, because like it's very easy to say this has nothing to do, like if you're aware that this is a problem, it's very easy to say this is like totally unrelated and just say there's no answer. And so they try to get something that's closer to a decision boundary, like the what year did Keanu Reeves direct The Matrix kind of example, where there's a false presupposition that Keanu Reeves didn't direct The Matrix, and so then it should be no answer. So it's like this whole Squad 2 approach of like, like if you want to probe the ability to detect failure to localize, then Squad 2 does the right thing.
So we've been using language models to train our
Mm-hmm.
part of the toolkit now.
Mm-hmm.
And so what are the implications for this methodology that we have now? Data uses logical objectives, different functions, and we hope that these models can overtake.
I mean, there are lots and lots of questions there. You could give whole talks trying to answer this. One anecdote, I work a lot with Samir Singh at UCI. He has some really interesting work doing it. It's something very similar to contrast sets, but like something like a unit test for different kinds of things. And one of them is like sentiments attached to named entities. So you can take a sentiment classifier and give it an input like, my flight to the US was awesome. Clearly has positive sentiment. Model predicts positive sentiment. If I change the US to your favorite country that typically has negative sentiment in English text, like maybe Iran, for better or worse, probably for worse, but so this has negative sentiment in large language modeling corpora. You change US to Iran, and the model all of a sudden predicts negative sentiment. This is clearly a very serious problem. You can do this with person names, right? Yeah. I guess what I'm thinking here about is just evaluation. How do I diagnose the problem, and in particular kinds of like language phenomena problems? And I would say the answer is just better test sets that actually capture the kinds of bias that you care about, whatever those are. I've built them around particular language phenomena. You could also build them around different kinds of bias. I want to be sure that when I'm evaluating these things, I'm detecting problems like this. Training models that don't have these problems is an entirely separate question that I'm not an expert in. I'm not the right person to answer that question.
Great talk. I have lots of comments, but time being limited enough. There's a comment about using experts.
Mm-hmm.
So people in the field that are doing lots of work with LPC
Mm-hmm.
are finding that the harder and harder the language problem becomes, the harder and harder it is to get any people to agree
Okay.
On an answer.
Mm-hmm.
And I've been looking at a lot of data, a lot of different tasks where I completely disagree with the annotations.
Okay.
Even though they're by experts.
Okay.
And so I'd be
Fair point.
I think there's a lot to be learned by crowdsourcing.
Yeah, I guess so. Our process for data collection has been, let me think about the phenomena, try to get away to pose an interesting problem in natural language that lets me do stuff that I couldn't do with a formalism, and figure out how to teach crowd workers to give me questions that actually probe this phenomenon, and then I will take stuff and perturb it a little bit as the expert to like get a comprehensive evaluation. And I definitely agree. There's a lot to be like. There's a lot of baggage here in like what I'm trying to say. Like natural language as an annotation format is very nice in that it lets me leverage crowd workers, I guess in ways that you're doing very nicely too with like this decompositional semantic stuff. And so yeah, I agree with all of that. That probably wasn't a very coherent response, but fair enough.
So the philosophy you have here is you want to focus on a particular phenomenon, so you engineer your data set to express that phenomenon. The alternative is just to get a much larger data set, and any phenomenon that doesn't appear in a larger and larger data set perhaps isn't important. So how do you resolve those?
So there's again a lot going on there. Let's take natural questions. This is a data set built by Google, where they say, let me build a data set around questions that people actually ask Google in search logs. And they say, because this is a natural distribution of questions, I'm going to get more realistic language, more realistic questions, and I know what things are important that I should focus on. This is great. I have no complaints about this methodology, especially if what you're trying to do is build a product that people are going to use and care about, right? This is fine. And there you have some measure of importance in some sense. I think when we're talking about language understanding, we don't have a measure of importance. I think what we care about is like anything, what I want to know is like competence. Anything that you could answer as a competent speaker of English, I want the machine to be able to answer. And thus, like, importance doesn't actually matter. I want to know, like, there are these different things that a person could be able to do. I want to measure, can a machine do them also? So does that answer your question? Yeah. Like, they're both good. They're answering different questions.
Do you think that we could like really systematically find ways to find these laws? Because like language is constantly evolving, culture, like different semantic patterns.
Yeah, like language change is a whole different area of stuff that's very interesting, very broad. I haven't thought about it very much, so I don't know that I'm going to give you a satisfying answer. I don't know that I can do better than that. One thing I thought about on this other question was no matter how big your natural questions data set gets, you will not know if you actually covered everything unless you do this systematic thinking.
If you think you can systematically enumerate it.
Fair point. There are things you can. And given that I can enumerate a bunch of things, I won't actually know if they're covered in my data unless I look.
So one way to improve your another way, I mean, so there's like all of the statistical machine learning that tries to like use theory to provide generalization bounds on our model, just giving training data and complexity of the model. Do you like think that has a role? I mean, obviously it doesn't work in deep learning right now because nobody knows what's going on with deep learning. But if we did have it, I mean, do you think that could solve some of these problems that we're facing?
So I think the generalization bounds actually work for deep learning. The theory still holds in like this IID test set. If I measure, like all of the bounds are still valid. My claim is that they are irrelevant for NLP. That's actually, that they're measuring something that we don't actually care about. IID is completely broken for NLP problems. That's my claim. Because when we talk about generalization, about language, what we typically mean is I want the system to do stuff that was not in my IID test set. Or that was not in my same distribution. I want to test things that are explicitly out of domain. And so this whole notion of IID test is just broken. And I think that's especially because we have this exponential input space. Just like things fall apart when you get this huge input space.